I'd like to talk about moment of inertia and try to use calculus things. The moment of inertia is the rotational inertia of an object, much like the mass is the linear inertia of an object. Pull my foot, or PL MI F tau, is a mnemonic that I like to use to remember a lot of equations of rotational mechanics. Whereas P is associated with linear momentum, the quantity F is associated with angular momentum, and the quantity F is associated with linear force. The quantity tau is associated with angular torque. Combining these with m for mass, let's just call that mass, and I for moment of inertia, I decided to change this back to their more standard names because inertia can sometimes be thought to refer to momentum or kinetic energy. But anyway, there are some relationships which can be converted over from linear quantities to angular quantities by just changing all the p's to l's, the m's to i's, the f's to taus, and one other change, the accelerations become angular accelerations, and the velocities become angular velocities. Here we have the equation for angular momentum, P equals mv, Newton's second law, that acceleration is the net force divided by the mass, and the kinetic energy equation, 1/2 mv squared, and finally, the impulse momentum law, force equals the impulse divided by time. Each of these equations has an exact analog in terms of angular momentum, L, moment of inertia, I, angular velocity, omega, angular acceleration, alpha, and torque, tau. The inertial quantity in the linear case doesn't have its own equation, it's just the mass. But the inertial quantity in the rotational case is the sum of all the masses times their distance, or radius r, from the center of rotation squared. So let's imagine that I have this three-armed spinner with 2 kilogram masses, each at the end of light 3-meter rods. If I wanted to find the moment of inertia of this object, first note that it depends on the center I choose. For instance, I could choose to grab hold of this rod here and spin it around this axis. That would give a different result than if I decided to hold on to this ball and swing it around this axis. So I'm going to start by imagining spinning it around the central axis and spinning it in the plane of the paper. So spinning it that way. In that case, the moment of inertia, as always, is the sum of the masses times their distance from the axis squared. That is going to be, for this guy, it's going to be 2 kilograms times a radius of 3 meters squared, plus for this guy, it's also 2 kilograms times 3 meters squared. And for this guy, it is also 2 kilograms meters squared. Whoops, squared. So that comes out to be 18 plus 18 plus 18 equals 54 kilogram meters squared. Just for the heck of it, let's compare that to one of the other cases. One of the configurations had the masses spinning in a plane perpendicular to the page. This one will involve a little bit of trig, so let's consider the angles first. The three-arm symmetry means that each of these internal angles is going to be 120 degrees to create that 360-degree circle. That makes this an isosceles triangle with two sides the same and one different. Since the sum of the interior angles of the triangle is 180 degrees, and 180 minus 120 is 60, then these two angles must be 30 degrees and share that 60 degrees. I'll split that isosceles triangle into two right triangles, and now I can use this distance is r sine 30, and this distance is r sine 30, and in this case r is 3. So I can use that to find out the distance from this mass to this mass is 2 times 3 sine 30 equals 3. No, that's not right. That needs to be a cosine 30. Cosine. It needs because I know that that line and that line are not the same. That comes out to be 5.19. Visualize that. 30 degrees, 5.19 meters. Another one at 30 degrees at 5 meters that we're spinning. And so we need to find which is going to be, say that's 5.19 sine 30. It was rounded incorrectly. But anyway, it comes out to be this radius, the distance here, r. Inertia for this is going to be I equals sum of mr squared. We're going to just say 2 times our mass, 2 kilograms, times, and that comes out equal to 27 kilogram meters per second squared. So when we spun it parallel to the plane of 54 kilogram meters squared, when we spun it on an axis on which both of those masses laid, that's exactly half. So I think if this guy were left out in space to its own devices, it would spin on both axes simultaneously. It would have a confusing rotational pattern because these two would be spinning fairly quickly, or it would be spinning along one of those axes fairly quickly, but it would also be spinning around group for the most part. If my understanding is correct, like in the vacuum of space where there's no other forces acting on it, a perfect solid will tend to spin on two axes as pretty often. On the other hand, if this was liquid, then it would quickly like the liquid would quickly go out to the ends of these, and you would end up getting rid of the smaller, the spinning around the smaller moment of inertia, and all the spinning would go into the mode of spinning with the greatest moment of inertia. In my next video, I'm going to come back and do what I promised to do at the beginning of this one, which is to do some calculus to calculate the moments of inertia of some various solids. Thanks for watching.